how's it going, everybody? We are here at the beginning of week 12, and this week we are going to discuss really two different topics. We're going to wrap up our ideas from chapter 10 that we had begun on 2 weeks ago, and we are going to introduce chapter 11, which is going to be our last chapter for the semester. It's certainly our biggest, bulkiest chapter of the semester. It will for sure take us all 4 weeks remaining to cover after we kind of introduce our beginning of it today or in our next video. So today we're going to cover sections 10.3 and 10.4, which is going to help us discuss polar coordinates in association with calculus here. We'll see that there's a few things that are a little bit easier to be done in polar, and that all the things that we've done in rectangular XY coordinates, we can also do in polar coordinates. So really section 10.3 gives us just our reminder about how polar coordinates work with a couple basics. Section 10.4 gives us our slightly more advanced ideas, our ideas about integration associated with polar, and we'll wrap up with all those guys here today. This won't be really too terrible to get through here. So first, a refresher of some basics from trig. Converting between polar and Cartesian is a super important thing to be able to do. Whenever anybody asks me for help with this, I am a sarcastic jerk, and the only thing that I do for those types of people that still are asking me those type of questions is I only draw a triangle, and then I don't tell them anything else, because this triangle right here should get you everything that you ever need to know for converting between polar and Cartesian. When we are in Cartesian coordinates, rectangular coordinates are grid coordinates. That's when we use measurements of x for width and y for height. So those are our natural labels for the perpendicular legs of any right triangle. When we're in polar coordinates, we are looking to describe the location of a point. So maybe I can say at this point right here is both the point x comma y or the point r comma theta here. We have a radius, that's the distance that our point is from 0, 0. And we also have an angle at which we are extending that radius, that's right there. Right? So using only this picture, we should be able to easily see all of the equations that are associated with converting between polar and rectangular. My first questions that I would ask are, in what ways can we use x and y to compute r and theta? Well, if I wanted to compute r knowing x and y, then I can use the Pythagorean theorem. That's x squared plus y squared equals r squared. And therefore, that gives me the formula here, r equals the square root of x squared plus y squared. Notice here, since we're talking about radius as being a measurement of distance, I'm only keeping the positive associated with the plus or minus that we have there. The other question is, if I knew only x and y, how would I compute theta? Well, relative to the angle theta, the side lengths of y and x are opposite and adjacent, so that makes me think tangent thoughts here. So my other statement that I could make is tan theta equals opposite over adjacent. That's y over x. And that leads me to the equation theta equals tan inverse of y over x. Right? So those are two of our equations here. But honestly, those are the ones that we need sort of less here. We want the ones that are going to help us go maybe in our other direction here. So our other two equations associated with this guy are, given only information about r and theta, can we determine x and y? Well, relative to the angle theta, x is adjacent and r is hypotenuse. So I'm thinking that there should be a cosine relationship in here. So I'm thinking here cosine of theta. Cosine of theta is adjacent over hypotenuse. That's x over r. And if we just multiply both sides by r, then we see that x is r cos theta. And similarly here, if we made a sine statement here, the sine of theta is opposite over hypotenuse. That's y over r. And I can multiply both sides by r to get y equals r sine theta. So these are the four equations that are used to convert back and forth between polar and rectangular. Those are things that you should absolutely have memorized. Absolutely, for the rest of your mathematical life, those are four equations that you should have memorized. And if you ever forget them, you should remember that the only thing you need to do to get all of that information back is just draw a right triangle and label it with the most generic labels you can possibly label it. X, Y, R, and theta. If you can put those four letters on a triangle, then you should be able to come up with all four of these equations, no problems. This is definitely an expectation that you know, not just looking up. Not like I can check that you're just looking these up, but if you're looking these up, you should feel me standing over you, shaking my finger at you and shaking my head. Know these. This is not hard stuff. This is just a right triangle description right here. So what can we do with these? Well, we can convert information that's in rectangular then into polar. So convert this gross equation in rectangular into polar, and then we'll graph both results in Desmos and kind of use that graph as our verification that we did the correct job here. So I want to convert rectangular into polar. So it looks like I want to take things that are currently in terms of x and y and turn them into things that are in terms of r and theta here. So it looks like my first move here is going to be to rewrite this side. I'm seeing an r squared cos squared theta plus r squared sine squared theta. That's all cubed equals 4 times r squared cos squared theta times r squared sine squared theta. So this is just my direct substitution line. I just only used these two equations in this box right here to do my direct substitutions. Let's see some things that are going to happen here, and hopefully you're super on board with the fact that this cosine squared theta plus sine squared theta equals 1 is going to be super duper helpful for us here. You should notice here, for example, we can factor out the r squared associated with this grouping. It will leave us just with a cosine squared plus sine squared, which means that's just really 1 r squared that we have. So this is really just going to be r squared cubed. Over here on the right, it looks like I have this coefficient of 4 is going to stick it out. It looks like we're multiplying up 4 copies of r, and I have a cosine squared theta and a sine squared theta. All right, so moving on here, it looks like on the left that's really an r to the 6th. I'm going to go ahead and divide by r to the 4th. And I'm going to very satisfyingly see that I do have a all squared stuff everywhere here. So now I'm going to take a square root on both sides, and I'm going to land at 2 cos theta. Oop. Uh-oh, okay. Backspacing is nice to me today. 2 cos theta sine theta. By the way, this is one of our Pythagorean identities. Ooh, man, I should even bring this up here. Let me do, ooh. All right, I'm gonna do a dumb thing here. Here we go, moving over to a different one here. Let me delete this. What? Remove. I don't need my face in here either. Remove. And let's go ahead and add window capture. All right, so here we are. We're looking at our trig function stuff right here. And we're going to need this a couple times today, so that's why I'm bringing it up right now. So what you should be seeing here is 2 cos theta sine theta. I'm seeing that guy. I'm seeing that guy right here. 2 sine theta cos theta is the same thing as sine of 2 theta. So I'm using our first double angle formula to rewrite this as simply as possible. So it looks like we got the thing on the right hand side here, and I'm going to substitute it with our most simple expression on the left there, sine of 2 theta as our final answer here. So let me come back to this guy here. So this should be r equals sine of 2 theta. All right. So it looks like we've come up with our final equation right here. Should notice a thing that's pretty typical here, by the way, which is that it's very typical in polar scenarios to write that r is a function of theta. Just like we say y is a function of x, it's typical for us to say r is a function of theta. This is typically the way that we write our function notation associated with polar equations, matching the way that we typically write it with our Cartesian. It's just not so obvious. Do we want r to be a function of theta or theta to be a function of r? As we know, it can go both ways. We could solve either equation for either variable that we wanted. Just a little bit more typical for us to use the r's and thetas as we'd seen right there. So let's verify that we did the correct thing here by popping over to Desmos and graphing each of these guys in Desmos to see that we are going to get this the same graphs right here. So our two competing equations here were x squared plus y squared cubed equals 4x squared y squared. And we're getting this 4-petaled flower that we're seeing here. We are alleging that r equals sine of 2 theta is the same thing. And what you can see here, oh my goodness. So I'm over here in my browser. I've been typing in my browser over here these things. Let me zoom in a little for us here. There we go. Now I can actually see my equations here. Calm down, Desmos, calm down. There we go. So what we can see here is I've typed in the first equation in blue, and I am getting that graph in blue. I've typed in the second equation in green, and we can see that these are going to be the same looking equation right here. I'm seeing that these graphs are sitting right on top of each other. I've got my green and my blue graphs right here. So I feel pretty dang good that these are indeed matching here. One thing I'd like to point out, by the way, maybe you can see this at the beginning, at the center right here. You should notice that the x and y equation is struggling a little bit to finish the graph. The blue graph here is struggling to go all the way to the origin. I know this is tough to see on your end probably, but the green graph is having no problem following these lines all the way into the origin, whereas the blue one's kind of making some V's out here. It's kind of struggling a little bit to handle this graph in Cartesian a little bit more than it's struggling to handle this graph in polar. And that's not a surprising thing when Desmos has to handle this stuff numerically here rather than exact. But in any event, this is excellent evidence that we did the correct conversion here to convert this gross equation in x and y into a very clean equation in terms of r and theta right there. So coming back over into what we got over here now, what I am interested in doing is doing some calculus things with this guy. For example, I am interested in finding the slope of that above curve at the location pi sixths root 3 over 2. So what you should notice here is that these are clearly an r theta ordered pair, not an xy ordered pair. And so it looks like we want to evaluate the whatever the slope equation, the derivative of this function is, at that r theta location. So notice here, we technically, we could go ahead and find dy dx in rectangular up here. You could do your implicit differentiation, and it looks like you'd get a chain rule as well as a product rule on the right, a chain rule on the left, chain and product on the right. You could solve for dy dx collectively and hopefully solve for dy dx there, right? It would take a little bit of algebraic work there, certainly, but technically I think we could do it. Notice that this equation is obviously way easier for us to manage some calculus ideas with. So let's go ahead and kind of see how we can, technically we can answer this equation not in polar if we wanted to. I guess that's what I'm getting at. But that is not going to be useful for you. It's going to be way, way, way better for us to do this guy in polar. And I know that just by comparing these equations. That equation in polar is way worse than this equation in polar. Also, our point was given to us as r theta. If we wanted to do this in terms of xy, that would also give us the added step of us needing to go back to our conversion equations here and computing the associated r or xy values to go with the r theta values over there. It's just work I'm not interested in doing. So it seems like what we want is we want dy dx. But the point is, I have no interest in attempting to solve that original equation for y. I also have no interest in doing implicit differentiation if I think I can avoid it. So here's kind of what I'm thinking. We want dy dx. We have that y equals r sine theta and x equals r cos theta. And we know that in general, we like to refer to our equations as r equals as a function of theta, right? We want to reference these as r being some function of theta, and that's what we see right here. R is a function of theta, just like we say that y is a function of x. Similar statements out there. So it seems like what we can do is we can do our derivatives that we learned associated with our parametric equations. It looks like this equation has been parameterized in terms of theta. X can be rewritten in terms of theta. Y can be rewritten in terms of theta here. So I'm going to rewrite my dy dx then as dy d theta dx d theta. So what's dy d theta? Well, y is r sine theta, and maybe it's going to help us to think of these like this, by the way. right? Remember, we're thinking that our r is going to be a whole function of theta. And again, that's exactly what we're seeing right here. R is a function of theta, right? This is not a weird statement for me to make. It's just slightly less comfortable for us because we're just slightly less comfortable in polar form here. So it seems like to perform this derivative here, dy d theta, I'm going to take the derivative of y with respect to theta, and you should notice we're going to get a little bit of product rule right here. First, I'm going to take the derivative of the f of theta and get f prime of theta. Then I'm going to leave sine alone. I'm going to add to that. I'm going to leave f of theta alone, and I'm going to take the derivative of sine and get cosine. In the denominator down here, same deal. I'm going to take the derivative of f first and leave cosine alone. Then, and notice here, I'm thinking ahead. This should be an addition for the product rule, but I can see that I'm going to take the derivative of cosine here, and I'm going to pick up a negative. This is going to say now leave f of theta alone and take the derivative of cosine, and that's what gives me negative sine. And that's how I knew to put the minus sign right there, even though that was a product rule, right? So it looks like we now have a way that we can go ahead and take derivatives in polar form right here. This is just our general rule for polar form derivatives here. Where r equals f of theta. And so let's go ahead and use this equation here to help us out with what we have above. So we found that r equals sine of 2 theta. And let's go ahead and use that in this equation here. And we'll find dy dx. And then we'll go ahead and evaluate it at the specific r theta place that we were given. So it looks like in our case here, we first need f prime of theta. And f prime of theta, it looks like it's going to be cosine 2 theta times 2. So 2 cos 2 theta times just the sine of theta here, plus f of theta was sine of 2 theta, and the cosine of theta gets left alone, all divided by f prime of theta is going to be the, f prime of 2 theta, again, is 2 cos 2 theta. We're going to see this is times cosine of theta here. Plus, oops, excuse me. Oh man, I'm not going to trust the erasing today. Minus f of theta is sine of 2 theta, and we get a sine theta associated with this guy here. So now that we have our derivative dy dx, we can now go ahead and evaluate this guy. And notice here, we don't even have any r's in here, so it looks like we're okay to evaluate this guy just knowing that one theta value. Oops, it looks like I've got my, I'm noticing here, I kind of wrote this backwards here. That's clearly our theta value. This is clearly our r value right here. Come on, computer, you can keep up. Keep up with me, please. Can I write still? Okay, it's writing. So it looks like my angle of interest here was pi sixths. So let's go ahead and throw pi sixths into this thing here. And so 2 cosine pi thirds, because it was doubled, times sine of pi sixths plus sine of pi thirds cosine of pi sixths, all divided by 2 cos pi thirds cosine pi sixths minus sine pi thirds sine of pi sixths. All right, let's just evaluate these guys and we are good to go. Cosine of pi thirds is our steep one there, therefore has a very short width. That's the width of 1/2. Come on, pen, you got to be able to keep up today. Sine of pi 6, this is our small angle, and it wants the height, and the height is the shorter part, so that's also going to be a 1/2. Plus the sine of pi thirds, at the height when we're opened up more, that's our root 3 over 2. And cosine of pi 6, that's our width when we're at our shorter of our two angles there. That's also going to be our root 3 over 2. All divided by 2 times, and it looks like we're getting our cosine of pi thirds, again, is our width here, that's 1/2. Cosine of pi sixths down here, it's our width here, that's root 3 over 2. Minus sine of pi thirds, that's our larger of the two heights there, it's root 3 over 2. And sine of pi sixths, that's our height here, it's going to be 1/2. And so what are we getting in total here? It looks like that's 2 times a quarter, it's just a 1/2 right there. 1/2 plus 3/4, all divided by 2.5 cancel. I'm getting root 3 over 2. And over here, I'm getting just minus root 3 over 4. And so what is this going to be right here? It's going to be 5/4, all divided by root 3 over 4. And so I'm getting here 5 over root 3 as our overall slope at that location right there. Verify this guy. Wasn't this the one? Is this the one that I pulled from the book here? Can't even find it. Oh no, this was not a book example. Okay, never mind. I thought I was verifying my answer in the book here. I'm not. Okay, so I'm seeing that 5 over root 3 as our slope at that given location that we're seeing right there. So we can compute these slopes here. And again, notice that to compute a derivative in polar form is just using our same parametric ideas. We have a parameterization for x and y in terms of theta and in terms of r. And so describing r equals f of theta as our format of our equation here, we can come up with what our general rule is right here. I guess I should put a box around this, right? That's in general. That's always the rule that we're going to get for derivatives of polar equations. If we're looking for the slope of a curve, we then applied the desired location of pi sixths as an angle and ended up computing our slope that was out there. So all this really is just an application of stuff that we saw back in section 10.2, right? Our parametric derivatives. We're just looking at the specific scenario of parameterizing in terms of polar terms here. So the slightly more exciting stuff here, I think, is our new calculus idea associated with this guy. So what we want to be able to do is find some areas that are bounded by polar curves. How do we perform integration to accrue area when we are given terms of polar coordinates rather than rectangular coordinates? Well, let's see exactly what's happening here when we do our rectangular things, right? Always reference back to the things that we know and then put this in terms of the things that we actually want. And if we're looking at any curve out here and we're measuring it in in rectangular, then what we know is that if we are to increase our x bound by a little bit so that we have a new delta x width right there, then what we've done is we've added on our new piece of area right there, right? That's our new area. And what we know, even though that delta x is really small down there, is that that new shape isn't quite a rectangle, right? It's not quite a rectangle because it's got some curvy top on top. But we know that as delta x gets smaller and smaller and smaller, the top of that curve is going to be interpreted flatter and flatter and flatter, because how much change could y possibly have if x is having essentially no change there, right? So we know that that's technically not quite a rectangle when we have a finite number of subdivisions, but as soon as we let the number of subdivisions tend to infinity, then each of those is more appropriately interpreted just as a rectangle area there. And so our new piece, our one new piece of new area, a single rectangle's area, was that f of x delta x. We let delta x go to 0 by letting our subdivision number go to infinity. And this said, now add up all of these rectangles with the height of f of x and a width of the infinitely narrow dx right there, right? And we did that from A to B. So all we really had to do to know how to compute the total area underneath a curve was to understand the idea of how much new area do you get when you increase the parameter of integration by a little bit. Here our parameter of integration was x, and so we said here, if you make x get a little bit bigger, then you've added a new rectangle's worth of area. If we think about adding up all of those rectangles, that's literally all the integral actually is just add up all the rectangles from A to B. we're going to think those same thoughts. But notice that now that we're not in terms of x and y, we are not accruing rectangular pieces anymore. So we shouldn't have this sort of x stuff times y stuff formation of our integrals anymore. In polar coordinates, we accrue new area by increasing theta. So now I've done this hand motion like a million times on video this semester. This is my dx integral hand motion. X is increasing and we're accruing new area. My new motion for polar form is that theta is increasing, and as theta increases, we are sweeping out new amounts of area associated with our curves here. So each new piece of area that's being swept out, before we interpreted this area here as the area of a rectangle, but you should be picturing to yourself, if we are sweeping out new area as theta changes, then we should be interpreting these as pieces of a circle rather than as rectangle chunks here, right? So what I'm picturing here is if we've got some polar curve out there, right, and we are starting with some initial theta right here, we can look at our new d theta right here. So I'm going to kind of do this as this is our delta theta, right? That is a measurable change in theta. It's still my delta, not quite my d yet right there. And again, what you can tell here is that this curvy part right here is not quite the curve of a circle, right? If this radius should have stayed the same the whole time, and it looks like it didn't in this drawing. But that's just the same thing up here as the top of this not quite being a rectangle. What you should be able to imagine for yourself is as delta theta gets infinitely small, by us breaking this up into an infinitely large number of subdivisions, that those two radii are going to get to be closer and closer and closer together to where it does make sense for us to approximate our new area here as a slice of a circle. Because these two radii, the different radii, as delta theta gets infinitely small, the difference in those two radii is also going to get infinitely small. And this will be appropriately represented as an area of a circle right there. So what is the area of one sector? Well, just picture a circle, and we're just talking about the area of one sector of a circle, right? If that was some angle theta that was sitting in there. So what I'm thinking is this is just a fraction of the area of a circle. So what I'm thinking is, oh my gosh, get out of here, writing. So our area of a circle, this should be our area of a sector, it should be pi r squared. That's the entire circle, but I only want to keep a proportion of that. Which proportion do I want to keep? Well, what I can see here is that theta is the amount of angle I've swept out in my sector. I know that if I were to get the entire circle, that would be out of 2 pi radians. That's the total amount of angle that's available. So the proportion of area that I've swept out is equal to the proportion of angle that I've swept out here. So this should be theta over 2 pi. And what I'm seeing now then is it looks like here we're going to be getting pi is going to cancel with pi, and I'm going to get 1/2 theta r squared, as it looks like this is my area of a sector. Now, what I know though really is that theta, this is really delta theta for us. Right? This is really my change in angle that I've experienced. That's really my delta theta that's associated with this guy over here. That's my delta theta in our case. So it looks like we have this infinitely small change in angle. And the way that we're going to interpret the area that we've accumulated here is going to be 1/2 times r squared times that infinitely small change in angle. That's our delta theta. That's going to become our d theta in our situation now. So now we're going to get here our total area is going to be the integral. So these are our theta bounds now. So maybe let me just call this theta 0 to theta 1, just to remind us these are theta bounds here. And it looks like it's going to be 1/2 r squared d theta. And again, delta theta in this equation became d theta in our integral that's down here. And finally, remember that R is our f of theta statement right here. This is like me saying y squared dx, right? If it was y squared dx, you know that you really need all x terms in your integrand. Here I have r squared d theta, so you know that you need all theta terms in our integrand. So it might be better for us to be writing this as theta 0 to theta 1 of 1 half f of theta squared d theta. And I think this is our more typical way that the book writes this guy right here. But it doesn't matter. This is just a more useful thing if we forget the typical ordering of which is a function of which when we talk about our polar coordinates. And again, r as a function of theta is the more standard way to go ahead and describe that there. So this is going to be our new formula for the area swept out by a polar curve here. And all we had to do that was to say, if the way that this works in rectangular is to build rectangular areas, then we want to add up an infinite number of rectangles where one of the parameters of the rectangle is infinitely small. Here, we do the exact same thing. We say the change in area, if we changed theta by delta theta, then the change in area should be described by this sector area approximately, if this was our average radius between these two different rays that we're seeing right here. But as delta theta gets infinitely small and becomes d theta, oh sorry, I didn't realize I'm falling off the side of my screen over here, and becomes d theta, then in that case here, we're going to be able to integrate across all of those angles that we see out here. 1/2, that comes from the fact that it was divided by 2 pi. That's where that 2 comes from in the denominator. This is really like our pi r squared, theta over 2 pi became our 1/2 r squared. This is our infinitely small change in angle that we're experiencing, our d theta that's out there, all right? So there we go. So we've got now a formula to accrue our total area that's been swept out. Now, there's one little technicality that we want to be very careful of here. Very importantly, we are no longer computing area under a curve. When we use the word under, that is us making a vertical comparison between two things. Under is a comparison of y values. You can't talk about under and talk about any value other than y. It's not an x thing, it's not an r thing, it's not a theta thing. That's a y thing, to be under something. We're not talking y stuff anymore. So talking about this as area under a curve is no longer appropriate. All right. So what we're going to see here, and I'm going to kind of highlight this in in the example that we do right here. We don't think of this as area underneath a curve anymore. That will lead you astray in this situation right here. So let's see what we're going to see otherwise when we perform this sweeping out of theta here. So what I would like us to do here is we're going to do from section 10.4, we're doing number 31 from like the homework problems out there, is I want to find the area that is between these two curves. That is the overlap. I'll just say that here. So I've been given two polar curves. I want to determine how much area is in the overlap of these two curves right here. So what you should do is the standard first thing we should always do in all parametric, all polar scenarios, and that's go graph it in Desmos and see what we're seeing here. What's not clear to me is where the overlap is going to be. It's not clear to me if there's going to be a whole bunch of symmetry or not. I guess I could kind of check that out with the equations right here. It's not clear to me what bounds of integration we're going to want. It's not clear to me how we're going to deal with the fact that there's two different equations right here. So I really have a lot of questions that are unanswered that Desmos is going to help me answer, like pretty much. Desmos isn't actually going to help me with one of the really important ones here, but we're going to be able to handle that one. So let's pop back over into Desmos and graph both of these equations and see what we see here to kind of answer some of our surrounding detail questions. So sine of 2 theta and cosine of 2 theta are the two equations of interest here. So coming back over here, I am looking at the two equations, r equals sine of 2 theta and r equals cosine of 2 theta. And so I'm seeing these two curves here. Notice that they're really kind of a very, very similar curve here, but one is sort of like a pi fourths rotation of the other, right? It looks like we rotated one of them by 45 degrees to get the other. That makes sense that it's a rotation by 45 degrees to get the other, because we know that the relationship between sine of theta and cosine of theta is that they are a 90-degree shift from one another, right? Sine of theta equals cosine of 90 minus theta. Here, since we are doubling the internal angle, we only need half as much of an angle of change to experience that transition. So that's why here we're seeing that one is only a 45-degree rotation of one another. So it looks like the location of interest, just to point out one of them, is this little sliver that I'm highlighting with my mouse right now. This is the overlap of area right here. What I can see is it does look like there are 1, 2, 3, 4, 5, 6, 7, 8 of these pieces that are all equal to each other. So one thing I'm seeing is it looks like if we can just identify this one like petal shaped with the corner sitting right there, wherever that intersection is, then we can just find that area and we can multiply that guy by 8 and we'll have our total answer here, right? So I'm seeing 8 of these little things. And again, I'm looking at the things that are coming together at like a point, not these smooth rounded outsides that we're seeing at the extreme edges right here. Just this overlap between the black and the purple curves is just this shaded area that we're seeing right here. So some things I am seeing here are, I know where the shape is. I know that there's a whole bunch of symmetry out here. I know that I can just find one of these slivers and multiply my answer by 8 because of the symmetry that I'm seeing out here to get my overall answer. What's not clear to me is what bounds of integration we're interested in using, right? If we're going to do an integral d theta here to compute some stuff, I need to know what angle we're hitting this intersection point at, and that's really not super clear to me. So what I'm seeing here for our picture, I'm going to do a terrible job of trying to draw this here. Oh, promise you I'd do a terrible job, right? We're seeing a diagram that looks something like this. I want this area that's in here, right there. That's our area of interest. Well, oh man, gosh. I'm going to come back over to Word now, and you're going to see the terrible diagram that I just drew. It's a terrible diagram. It's supposed to be reflective of this diagram. Okay, I'm going to do a smarter thing, and I'm going to erase what I just drew, actually, and I'm just going to copy and paste in the Desmos diagram, and then we're going to be happier with this right here. So I am going to come back over to Word, but I am going to, real quick, I'm going to go take a copy of this picture right here so that we can just use this picture. So give me one hot second here. Copy that. Come back into Word. Okay, Microsoft Word, was that a mistake? It appears to have been a mistake. We'll see if my computer starts responding again. Can I click? There we go, we're back. Okay. Remind me to never take snips during a video, apparently. It's not allowed. Okay. So here's our, together here, okay. You can do it. I promise you can do this, computer. I promise you can do this. So it looks like this is our region of interest. So I'm going to say here, we want 8 copies of that area. What I want to know is, where is that intersection happening right there? This point where they come together, where is that point? Okay. Shade this in a little bit. That's our region of interest, and I want this point right there. So to find that point, what I can go ahead and find is, it seems like I want to know the theta value at which the radii are going to be the same. Well, if at this point the radii are the same on each of the two curves, I can go ahead and set these equal to each other. So I'm going to find the intersection here by setting r, and I'm just going to call these r1 and r2 right here. And it looks like that's going to be sine of 2 theta equals cosine of 2 theta. And I need to solve this equation here. I see sines and cosines of the same parameter here that are equal to each other. I'm thinking I can do a little division here to solve for this guy. And that's going to lead me to be able to say tangent of 2 theta equals 1. I know that a tangent is equal to 1. Oh, I better reverse my idea right here. Whenever we are at 45 degrees or pi fourths, and then also at 5 pi fourths on the other side over here. So this is going to say to me, this is true whenever 2 theta is equal to pi fourths plus pi k. And then I'm going to divide this whole thing by 2, and we're going to get pi eighths plus pi halves k. It seems to me like this pi eighths is really the thing that we're looking for right here. So very importantly, what I want to do now is go back to Desmos and see if we're just looking at the 0 to pi eighths for each of these guys to recover the bounds of interest here. And here's what I'm going to see. When I come back over to Desmos now, I'm interested in, again, we're looking at for this pi eighths value here. So I'm going to go ahead and do pi eighths here. And what I'm seeing is, yes, that does look like that first piece of that lobe that I was interested in here. I'm going to come over here and I'm going to do the same thing. And I'm going to do pi eighths. And 0 to pi eighths, ooh, it does not look like that worked out right for me. Why not? Here's what I'm seeing. If my cosine equation starts at theta equals 0, I know that cosine of 0 is 1. So it makes sense to me that my initial location is actually here for 0 to pi eighths. It seems like I actually want pi eighths to be where this part of the curve starts, not where it ends. So maybe it's more appropriate for me to come over here and do pi eighths, but that means then that I've got to keep on flowing from pi eighths. Now, it's not super clear to me what I want right here. Notice if I, now by the way, notice this good thing. I'm starting at pi eighths and it is starting where I want, but it looks like going all the way to pi is too much. It looks like even going to pi halves is too much. It looks like going up to pi fourths is getting us exactly what we want. So notice here, if we allow our angle to go from pi eighths to pi fourths, that's going to bring us from our intersection location back to the origin. That's exactly where we wanted to be with this guy. So I can see here now my two, just be 0. Why are you going to make it all grayed out? My two bounds of integration that are associated with this guy for my integrals. So with some Desmos help, I have determined that I am interested in the bounds of integration being from 0 to pi eighths for the purple piece of the function, and from pi eighths to pi fourths for the black piece of the function, the cosine part of the function right there. I have one last little technicality to figure out before we go ahead and do the integration, and then we'll go ahead and actually hit some integrals here. All right? So I'm going to say here, okay, come on, mouse and keyboard, I'm certain that you're capable of doing this. Stick with me here, computer. By next week, I will have another new computer, and I think that one is going to work. I swear that one's going to be the one I want. So, what did we just learn here? So for the r equals sine of 2 theta, oh my gosh, I'm sorry. I'm over here in Microsoft Word again. From Desmos, we can see that we want bounds of, for the r equals sine of 2 theta scenario, the sine equation was the one that we saw went from 0 to pi eighths. And for our r equals cosine of 2 theta, it seems like the bounds of interest for that little chunk were the pi eighths up to pi fourths. Okay. Now, notice this one last little thing here that we want to think about. So here's where I want to convince you that your intuition will lead you astray if you try and only use your XY intuition here. This is a really important part. Every single time in your life up until now that you have computed the area between two curves, you have always done subtraction between the two equations. However, what you should notice here in this case is that if I integrate sine of 2 theta from 0 to pi eighths, can I now do the thing I always hate to do? Yes. Oh, thank you so much, Desmos. So what I am going to see here is, I'm going to draw just my first quadrant for each of these guys. And in fact, let's come back over to the browser real quick here and see this. If I look at this guy from 0 to pi eighths, and just the purple curve here, then what we're seeing is that, and it's not going to, now, oh man, all I want to do, by the way, is just do this, and Desmos doesn't support this. Of course they don't. I can't just draw a straight line. So instead, I need to do like y equals mx and add a slider so I can help you guys kind of visualize this right here. Oh, of course, that's not going to be any good for us right there, so. Okay, can I do it now? So here we go. So picture that red line right there as being like a dividing line for us right here. What you need to be able to see is that the area between the red line and the purple curve, that's what's getting swept out by us integrating from 0 to pi eighths, because we are starting at, we are starting at an, why can I not, I have to flip my camera horizontally, I can't do that. We're starting at an angle of 0 and sweeping out to this, whatever that slope is, whatever, 0.4. I don't care about that number for the slope. I'm just trying to get a line on the graph. Since we swept out this area by that curve, it is now this area that is between the red line and the purple curve. That's the area we've accumulated in our 0 to pi fourths integral of sine of 2 theta. Then what we're going to want to do is we're going to want to add on the area that is swept out. Notice that this curve is going to start at pi fourth or at pi eighths, and it's going to increase to pi fourths out there. So this area now between the red and the black curve is how much we will get from integrating cosine of 2 theta from pi eighths to pi fourths. So the super important thing to realize here is that integrals of polar things aren't area under the curve. So it's not like we want to do the black curve's integral and subtract off the purple curve's integral. That's not what's happening, because the integral of polar curves does not give you the area underneath the curve down to the x-axis. That's rectangular concepts, not polar concepts. Here we are sweeping out new area, and that new area is being swept out by theta. It's not an area under the curve thing anymore. All right. So as you can see with this red line being added on here, the first integral of the purple curve, the underneath curve, when we do the integral of sine of 2 theta from 0 to 8, that will get us the bottom half of this grouping. When we then do the integral of cosine of 2 theta from pi eighths to pi fourths, that will get us the top half of this grouping. So in this case, we really do want to add together these two integrals right here to get the total area associated with one like petal of this flower, of this 8-petal flower that we're seeing out here. All right. So I'm seeing here that this integral will be giving us our, sorry, let me do something real quick here. So our sine one was the off-centered one. So it's going to get us all this stuff that's down here. Ooh. Sorry, that's not quite right. Oh my gosh, backward anyway. It doesn't matter. I'm just going to keep on making the same mistake over and over and over and over today, apparently. Let me go ahead and try. Okay, so what I'm trying to draw here is that this guy is only going to give us this little piece of area that's down right here. And our other one is going to be giving us, now this guy was the one that was centered like this guy right here on the axis. And he is going to give us this little upper piece that's right here. So here, all right, so let's go ahead and do this guy here. So it seems like what our total area then is going to be 8 copies of what? We're going to get the integral from 0 to pi eighths of sine of 2 theta. Excuse me, need to back up here. That's not what we're integrating here. Remember that our formula here is 1/2. Come on, you can do this. I know you can do this. Pick it up, mouse. 1/2 f of theta squared d theta. So here I'm going to just pull this 1/2 out front. I've got my bounds from 0 to pi eighths of here. This is really r squared, right? So this is going to be my sine squared of 2 theta d theta. And I am adding that. I want more area because we've accumulated the bottom half of our petal. I also want to accumulate the top half of our petal. And this should be of cosine squared 2 theta, right? D theta. And this should end up giving us our entire area, right? 8 copies of the bottom half of the petal plus the top half of the petal is what I'm seeing right here. Each of these is just directly using our area formula associated with area with polar curves here. So one thing right away that I'm seeing is I can clearly factor out the 1/2 on both of these guys to just get a coefficient of 4 that's sitting out front. But it looks like I'm going to need some help here with my sine squared 2 theta d theta and my cosine squared 2 theta d theta. And this is from 0 to pi eighths, and this is from pi eighths to pi fourths. Okay, computer, if you're going to bail on me, you got to wait. You just got to wait, computer. I need to get through this. All right. So how the heck are we going to do these two integrals right here? How are we going to do them? We are going to very smartly search up and down to find, hey, there we go. Looking back over here. So I need some ways to replace sine squared and to replace cosine squared. And the way that I think that I'm going to do that is I am looking at, I guess I see, oh my gosh, get out of here. I am seeing these two equations right there. I see a way to rewrite sine squared in terms of a cosine of a double angle, and I can rewrite cosine squared in terms of a double angle. So it looks like those two double angle formulas are going to be what I want. So I'm going to copy them both down, and then I'll move back over to Word. So it looks like my one that's going to help me out with cosine is cosine of 2 theta equals 2 cosine squared minus 1. And my equation that's going to help me with the sine squared is cosine of 2 theta equals 1 minus 2 sine squared theta. All right, so I'm going to pop back over into Word now. All right, so those are the two equations that I just copied down from my equation sheet. And here's the really important thing to notice here. Here, notice that sine squared of 2 theta is what we have. Over here, there's just sine squared of a single theta, and it's going to result in a cosine of double that angle. Here, my angle is 2 theta, so we're going to double that to get 4 theta here. So I'm noticing here cosine of 4 theta is 1 minus 2 sine squared of 2 theta. Similarly here, cosine of 4 theta is 2 cosine squared 2 theta minus 1. And now I can go ahead and solve for the needed sine squared 2 theta, cosine squared 2 theta associated with each of these. It looks like here I'm going to get a 1/2 cosine 4 theta minus 1 equal, and that's going to be equal to my sine squared 2 theta. And over here, similarly, I'm going to get a cosine squared 2 theta. I add the 1 over and divide by 2, so I'm going to get a 1/2 of cosine 4 theta plus 1. All right, so now I've got my trig substitutions that are going to help me actually do this integration here. So now it looks like I can come back to my area statement here. It looks like I'm going to get 4 copies of the integral of 0 to pi eighths. The 1/2 is going to come up front, and I'm going to get a cosine of 4 theta minus 1 d theta. And I'm going to add that to, again, the 1/2 comes out front, pi eighths to pi fourths of cosine 4 theta plus 1 d theta. All right. Once again, I'm seeing that these 1/2s can be factored out front. And now I just got to do some integration here. So I'm going to switch to brackets here for this guy. So I'm doing a couple steps here. The 1/2s are getting factored out front to hang out with the 4, so that's now a 2. I'm going to do each of these sets of integration in here. So I'm going to now get the integral of cosine of 4 theta is going to be 4. Oh, wait a minute. It's going to be, oh, let me just back it up then, and I cannot trust my backspace right now. So let me get my eraser. The integral of cosine is going to be sine. But I know that if I were to take the derivative of this, it would pop out a 4. I need a 1/4 to cancel that out. Minus integral of 1 is just theta. And that's going to be evaluated from theta equals 0 to theta equals pi eighths. Then we are adding to that a very similar statement here. We're going to get a negative 1/4. Oh wait, no, we're not. We're not getting a negative anything. The integral of cosine is sine. It's not a negative. And that's going to be plus theta. And we're going to evaluate this guy from theta equals pi eighths to theta equals pi fourths. All right, let's just evaluate, and we are cruising here. So, what am I seeing here? Oh, come on, pen, you gotta pick it up here. Let's go with it. So I'm seeing here 1/4 of, so I'm plugging in pi eighths into sine of 4 theta. 4 copies of pi eighths is pi halves. On, pen, come on. You got to be able to keep writing here, buddy. We're not even, we still got a ways to go. On our second grouping, our upper bound is pi fourths, so we're going to get a total of pi in there. Minus the lower bound at pi eighths. Plugging in pi eighths, multiplying it by 4, we're going to get pi halves plus pi eighths. That's our other grouping in. So now we can go ahead and do some evaluating. I'm noticing that this group right here is all just equal to 0. Over here, what are we getting? Sine of pi halves is 1. So this looks to me like it's 1/4 minus pi eighths. On our second grouping here, we're getting sine of pi is 0. So I'm getting pi fourths minus what am I getting here? It looks like this guy is going to be, wait a minute. Now I'm confusing myself. Yeah, that minus that I wrote right there is included right there. It's our subtraction symbol for the entire grouping right here. This is going to be 1/4 sine of pi halves. Well, sine of pi halves is 1, so I'm going to get a minus 1/4 here. And it looks like we're also subtracting off pi eighths. And so what am I in total seeing here? Of course, I'm seeing something that doesn't match what's in my notes right here, so give me 1 second so I can look at this. I think that I made an algebra mistake back up here with my trig parts. I guess I'm going to fix this now. That's not true. Did I copy these down wrong? How am I getting different things then? Cosine of 2 theta. That's correct. I'm going to add the 1 to the other side. And I'm going to divide the whole thing by 2. Over here, I think I have these flipped. I think I have a wrong sign right here. This should be a 1 minus cosine 4 theta. So here's the mistake that I made. I dropped a sign in there. Fortunately, this should just be equivalent to a negative being dropped, right? It's just a factored out negative that I've missed here. So I believe it's the case that I can just add in a negative here. I'm going to stick it out with red. So I'll make that a negative, just a negative on these parts. In total, just a negative from this grouping here. It's still not, seriously, did it not just write, and then keep it there, thank you. These still aren't the terms I'm coming up with here, so let me kind of, I think I got flustered here and started making some mistakes. Pi eighths, 4 times pi eighths is pi halves. Oh, I'm talking myself out of that. So I should be getting pi eighths minus pi fourths. That's all good for our first grouping. For our second grouping, I should be getting pi fourths minus 1/4 minus pi eighths. Okay, I think I've got this all correct here now. Okay, that was only 1 drop negative right there. That wasn't too bad. Oh, go ahead and bring that red with me. Thank you. So what am I getting here? Pi eighths minus 1/4 plus pi fourths minus 1/4 minus pi eighths. So I'm seeing here a pi eighths and a pi eighths are going to cancel. it looks like I'm getting pi fourths minus a half times 2. Pi fourths minus 1/2 times 2. That's going to give me pi halves minus 1 as the total area of all 8 of those lobes that we're finding out there. All right, there we go. I managed to actually get to the right answer despite making a bunch of mistakes along the way right there, or getting flustered either way. So we now have an area of those intersecting pieces, all 8 of those things. We identified one of them. We summed 2 integrals to get its area. We multiplied the area by 8 to get all 8 pieces. So this is now the area of overlap between those 2 polar equations that we've got right there, pi halves minus 1. All right, let's just take a look at one more example here and we'll call it a day. And I know that my computer is just going to work nicely and I'm not going to get flustered on this one, so we're all good to go. The last one that we're going to look at is actually the book example. And the reason I'm going to do the book example is because the book just abandons the example. And they're like, and you could just ask the internet what the answer is. And that's obviously stupid. I want us to actually be able to do the integration here. So let's set ourselves up to be able to do that. So what we would like to do is find the length of a cardioid. Cardioid is one of the standard shapes that we'll end up seeing from lots of polar shaped curves. We're going to let Desmos instruct us what a cardioid looks like here. And we want to find the length of that curve. So that sounds to me like an arc length scenario here. So r equals 1 plus sine theta. Let's go over into Desmos and see what that guy looks like. R equals 1 plus sine of theta. And so this is a cardioid. In general, you can see that this is sort of vaguely heart-shaped, which is why it got the name cardioid. If we were to flip this guy upside down here or something like that. And so I think that's at least a sensible name here. We should be able to see, by the way, this thing has been really not, yeah, so for some reason you can't, I can't seem to do parameters in here anymore, which is very frustrating. Can I do this and make a interval for A? No, not allowed to do parameters anymore. So in any event, the point is you could see here, if I want to find the length of the entire cardioid, one of our questions should be, what should our bounds of integration be? I can see that if I just have pi, that doesn't get me the entire shape. If I do 3 pi halves, that's getting me most of the shape right there. And in fact, you can see it's getting me 3 of the quadrants in which the shape lives out of the 4. So therefore, if I go to 4 pi halves, we've now swept out that entire shape one time. So it does look like 0 to 2 pi is going to be our appropriate bounds of integration that are associated with this shape. So we're interested in an arc length computation. I know that theta should go from 0 to 2 pi to identify the length of the entire shape. What we are going to need to do is we need to go ahead and update our arc length equation so that we can actually do this thing here. So let's go ahead and update this arc length equation. I think we have audio back now. Is that true? Yes, we apparently have audio back. Okay. Seems like we might have audio back. I'm going to trust that we do. So when we're talking arc length in parametric, we were given the integral of, and this one worked out really nicely, to just be, we got our general equation here in parametric. I talking myself out of this guy right here. So is our like dy dt plus dx dt, and each of these guys were squared. Our parameterizing variable in this case was the t. Right? In our case, our parameterizing variable is going to be theta. And so what we're going to look for is dy d theta and dx d theta, and the integral will be d theta. So for polar arc length, we are going to get from theta 0 to theta 1 square root of dy d theta squared plus dx d theta squared d theta, right? So all we want to do is come up with a simpler expression for what this actually is right here. So let's go ahead and do the same manipulation inside of this integrand as we did up above when we did our derivative up there, and we will be good to go here. So we previously already found that dy d theta, right, when we have that y equals r sine theta. It looks like what we're getting here, and remembering that we're really thinking of this as f of theta sine theta, is that dy d theta should be f prime of theta sine theta plus f of theta cos theta. And we've got that dx d theta when we're thinking of x equals r cos theta, or more appropriately, x equals f of theta cos theta. That we're going to see here, we're going to get the derivative of f. And I know that minus sign is coming up. We are doing the product rule here, but that minus sign is going to be coming from the derivative of cosine as negative sine of theta here. All right. So I've got dy d theta, I've got dx d theta. I need to square both of these and add them both together. So what's our square root term going to look like here? So what do we get underneath the square root here? I'm going to square the first grouping of terms. So I'm going to get df d theta squared sine squared of theta. That's the first term of the first group squared. Plus, we're going to get 2 copies of the second term. First term times the second term. Plus the last term squared. That's our first term squared. Let me... is it not going to... Okay, it's happy with me. Okay, and we're adding to that why does it keep wiping away what I'm writing? Still under square root. Our second term squared. Our second term was our dx d theta. We're squaring this guy also. And so I'm going to get our df d theta squared sine squared of theta. We're going to get 2 copies of the product of both, but notice that when we got the minus sign from this product rule here, that means we're going to get a minus 2. Minus 2 f of theta, f prime of theta. Oh, wait a minute, didn't I? I did make a mistake here, didn't I? I'm making more mistakes. What do you know? It seems like here we took the derivative of f, but we should have left cosine alone. That is a... Stop erasing what I'm writing. Oh my gosh, what's happening here? That's a cosine right there. So this is 2 times f prime times cosine times sine. And we're squaring the last term, so that'll be plus f squared theta sine squared theta. So here's what you should be noticing here. This is really our whole thing underneath the square root right here. Here's my stuff to notice. Oh, and by the way, this is now wrong. That's our cosine squared of theta right there. All right. The thing I'm noticing that's super nice is it looks like our cross product terms are going to cancel out completely. And it'll just keep on deleting everything I'm writing right after. That's really convenient for me here today. So that's really nice. The other thing that's really nice here is I'm noticing that we're adding up some sine squared plus cosine squared stuff and some sine squared plus cosine squared stuff. In both those cases, when we do the factoring out, that's going to leave that as just a 1 multiplier times that stuff. So I'm seeing here, we are getting a df d theta squared sine squared theta plus cosine squared theta plus, and over here it's just f squared of theta sine squared theta plus cosine squared theta. In both cases, sine squared theta plus cosine squared theta becomes 1. And so it looks like all we really need is just the derivative of f. And remember, we said that f, that's really literally just r. So it looks like this is the derivative of r with respect to theta plus f is literally just the radius. So it looks like this is our new arc length formula. And we got that just by subbing in our derivatives right there. I just took my new derivatives and subbed them on in, and we got the new terms that we were interested in there. So now that I have my new arc length formula, let's go ahead and do that for this cardioid here. So we were given the cardioid r equals 1 plus sine theta. We determined from Desmos that we needed all of 0 to 2 pi to get its length. So I'm going to do the integral from 0 to 2 pi of the square root of, now, dr d theta squared. Dr d theta, in our case, is just cosine. And so it seems like I'm going to be getting cosine squared plus r squared. Notice that r squared here is 1 plus sine theta squared. And I put my squared in the wrong spot here. It's all of 1 plus sine theta that's squared. And that is d theta. And so I need to expand this guy. So this should be 0 to 2 pi square root of cosine squared theta plus 1 plus 2 sine theta plus sine squared theta. That's all d theta. So what I'm noticing here, notice that cosine and sine are going to add to give me 1. 1 plus the pre-existing 1 makes 2. So this is where the book just stops and says, and you can sort of just look it up that the answer is going to be like 8 or something. And I find that highly dissatisfying, which is why we're doing this problem. And we're going to actually do this integral here instead of bailing on it and just cheating and looking it up in Wolfram Alpha. So let's go ahead and do this here. So the one thing I can at least see is that it looks, or I would be able to see if I was allowed to write, is that it looks like there's at least a square root of 2 that I can factor out from this thing to give me 1 plus sine theta underneath the square root here. So let's go ahead and see a little sneaky technique we can do for this one. My problem here is that I don't really have like a 1 plus sine theta that becomes the square of something. If we come back over and look at our Excel thing over here, like I don't have, or sorry, Excel, our PDF over here of our trig book, I don't see anything that gives me like a 1 plus sine theta. A 1 plus sine theta, I don't see anything that's over here. I was kind of hoping for one to crop up in these half angle formulas, but these all involve like 1 plus or minus a cosine, it seems like. I don't ever see like a 1 plus sine theta out here. So my issue here is it doesn't seem like there's an easy way for me to get at this with the stuff that I've already got. So what I know is I'm going to want to screw around with how this thing is currently formulated to make this work out a little bit different for me. Other things that I know is that the square root is kind of bothering me here, so it would be cool if we ended up with some squared stuff. So how do we get squared stuff when we have an addition? I like to use conjugates in this case, so here's what I'm going to do, or what I'm going to try to do. We've got this 1 plus sine of theta here. I'm going to go ahead and hit this guy with a 1 minus sine theta over 1 minus sine theta. And this is my conjugate that I'm multiplying by here. What this is going to do for us up top is it's going to give us 1 minus sine squared of theta over square root of 1 minus sine theta. So we're still going to be left with that stuff on the bottom, but what we've now done is we've now introduced for ourselves a cosine theta on top, and that's going to help us make a substitution here. The real issue is that I can't do like u sub with the original because I don't have like a cosine term to partner with. So by multiplying by a conjugate, I have introduced a cosine term that I can now partner with to do some u sub. So now I'm thinking to myself, I can now make a u, something like 1 minus sine theta, and use the du of negative cos theta d theta. And that's going to allow me to now make my substitution happen. So I'm going to get a negative root 2 integral from 0 to 2 pi of 1 over square root of u du. Notice that that negative sitting out front, that came from my negative in front of the cosine that's right here. So I'm going to rewrite this a little bit more smartly as u to the negative 1/2, because I want to use the power rule here. And that's going to give me, I add 1 to the power to get u to the 1/2. If I were to take the derivative, it would pop down a 1/2, and I don't want half of it, I want a whole thing. So that means I've got to introduce a 2 as a coefficient sitting out front here. And, yeah, right? And now I'm evaluating this guy from, very importantly, from theta equals 0 to theta equals 2 pi. Don't lose track of the fact that we've converted into u here now. So I am now getting, why do I feel like that's not matching what I'm supposed to be getting here either? Where's this? Oh, I see. When I did that earlier, I dropped. Okay. So I'm seeing here, negative 2 root 2 square root of 1 minus sine theta, evaluated from theta equals 0 to theta equals 2 pi. I don't really understand our negative now. This is very disappointing. Why am I getting... Okay. Well, in any event, I did the integral that I wanted to here. I just got to wrap this up at this point. Plugging in 2 pi gives us 0. Theta gives us 0 here. So what we're going to get is we're going to get... what's... Okay. I don't understand where I went wrong with this example, but I've got to just call it right there. I'm at an hour and 23 minutes. Apparently, I'm not able to find the arc length of a cardioid, but at least I can do an integral here. I'm going to wrap it up since I'm way more interested in us moving on to sequences and series here. If I give you any arc length problems, they'll be easier than this one. I'm going to call it a day here, and I'll see you guys for our introduction to sequences in the next